sound, so while we're getting that set up, we're going to be streaming over the phone. Now, we posted a note on Piazza asking you for topics that you thought might be worth revisiting. And of the 200 odd people in the class, only about, I don't know, 30 or so responded. So I'm not really sure that's worth our time, but nevertheless, we'll spend the first 15 minutes or so going over some of the topics that we've already covered. And this is your opportunity to ask questions. We can go back on Piazza afterwards, but sometimes it's just easier to discuss these things in class, right? So, the first thing, gradient descent and backdrop. There were some questions on gradient descent and backdrop in general. I'm not really sure what the confusion was. But here is the basic idea behind gradient descent, just to recap. If you have a function of this kind, some f of w, which we are trying to minimize, and if you are performing an iterative estimate of the value of w where this function takes its lowest value, right? So if you're trying to find this location, you would start off at some point and keep adjusting your w till you got to the bottom. And the basic rule we're going to apply is that if your current estimate is out here, say, then at this point the slope of the function is negative. If the slope is negative, you want to increment the weight. In other words, you're going to be subtracting some scaled version of the slope because the slope is negative, so minus and minus becomes positive. On the other hand, if your current estimate is out here, the slope is positive, which means going forward is going to increase the value of the function, so you're going to walk backwards. Once again, now the slope is positive, you're going to be subtracting some scaled version of the slope to walk backwards, so that you can actually head towards the minimum. So the overall gradient descent rule in vector form looks something like this. If wk minus 1 is your current estimate, your kth estimate is going to be wk minus 1 minus some step size times the gradient, right? Now keep in mind that the step size is multiplying the gradient. The step size is not the size of the step you're taking. The size of the step you're taking is a product of the step size and the gradient, and this will influence some of our decisions downstream. So when we are training the neural network, again, we had questions about backdrop and gradient descent in general. So we'd have a collection of training instances. For each training instance x, we would have a desired output b, and f of x semicolon w, this term over here represents the neural network itself, where w are the weights, the parameters of the network. So for each training instance, you can define a divergence between the actual output of the network and what you want it to be. This is a function of w. You average it over all of your training instances, and now you define a loss, and you end up with this loss function, which is a measure of the average error between the output of the actual output of the network and the output that you want from the network over all of your training instances. And we will try to find the weights, the parameters, which minimizes this average error. So now once you've defined your average error, which is a function of the weights, you can actually define the gradient of this loss with respect to the weights. And the gradient of the loss is simply going to be the average of the gradient of the divergences for the individual training instances with respect to the weights. Simply because gradient is linear, it just moves into the summation. And what we will actually do is to use that gradient in your gradient descent rule to estimate your weights. And this term over here, the gradient, so the only term that needs to be computed once you write it like so, is this term here, which is the gradient of the divergence between the desired output and the true output of the network for individual instances. We would have to compute this divergence term, the gradient of the divergence for each training instance, average them all, and that's going to give you the overall gradient of the loss function. So this term is what we will compute using backpropagation. Now backpropagation, we've been through this before. For each training instance, again, going back here, we need to compute this gradient for each training instance. So for each training instance, first we're going to pass the training instance through the network. And I'll explain the whole process in vector form because it should be fairly simple. If my training instance is X, the input to the neurons of the first layer of the network is simply going to be the weights times the input plus the bias. I've written this in vector format. So the weights for the first layer can be written as a matrix. If I want to write this out in scalar form, this is going to look like Zi, which is the I input. Actually, I feel like this is Z1, comma I, because we have the 1 over there representing the first layer, is going to be summation over J, W, I, comma J, Xj, right? So basically, all of the weights for the first neuron. And we have a collection of these guys. This entire thing can be represented as a